Okay, so I guess first things first, I'm recording this on Zoom because several of your classmates are sportsing, they're baseballing and soccering and things like this, right? So we have a lot of people missing today. Okay, so before we start, any questions or concerns from last time? Anything on your minds? Okay, just real quick, a sort of schedule announcement here. So if you look at the original schedule, there was a exam slotted for Friday of next week, but I was thinking about what next week should look like. I don't really know what to do about these spring break days, right? So for me, a break day like Easter break, it's like, oh, sweet, I can catch up on work. Like for me, break days are always work all day, and that's nice because now finally I can just work all day. Like I can catch up on grading or whatever. But I assume that's not the intention for you people. Or maybe that's what you do. I don't know. Anyway, so I felt bad about having an exam the end of that week, where in theory you have 2 days off. So instead, we're just going to lose a day essentially. But again, I didn't. The intention of the school, right, is that you have breaks on those days, right? So anyway, I felt like we couldn't really have breaks on those days for you guys if we had an exam on Friday. So if you look at the schedule for next week, you'll notice that it's just kind of padded a little bit. So we're going to practice with Laplace transforms all day Wednesday, then an official review on Friday. So the original schedule has those like up a day. And then the exam will be the following Monday. So if you look at the Monday for this upcoming Monday, that's why I have the exam review stuff posted there. So I always post the exam review stuff a week out. So that's why it's posted there. Okay, so last time we walked through this problem, which from a global perspective, from a zoomed out perspective, is super nice. I mean, now we can handle these discontinuous forcing functions that we couldn't handle before. Now at a granular detail level, the problem is a huge mess, right? Well, remember that mess? You're like, oh, I gotta divide by root 15 over 16 here, and then multiply by root 15 over 16 over here. There's all these little details, right? They're kind of obnoxious. So anyway, but again, it's easy to lose the forest through the trees, but if you keep your eyes focused on the forest, it's really nice what the transform is doing for you. So of course, we're not going to rehash all the details of this example, but as I pointed out last time, if these are what solutions look like, you're going to pay a price getting there, you know, and that price is this detail manipulation, you know. This problem as written, though, of course, is not like an exam question, right? Because on an exam, there's time limitations, and I don't know. The numbers just have to be nicer than this on an exam. So here's a question that's more like what you see on an exam. So I want you guys to do this maybe 10, 15 minutes. But before we do, let's scroll down to the solution. See this solution? If that's the solution, you can already see that like there's probably not going to be so many algebraic manipulations and massagings, right? Not so many details. So take maybe 10 or 15 minutes to try this. I'm going to walk around and see what you guys think. So Hema and Pedro, I'll come check in with you after I'm done walking around.
Oh, it is too. I misread that about masks.
Yeah, it's not math.
So it's going to equal 2 times what it is to 200.
So what this means is no force of one turn on five.
So it was never turning on and off.
That's what turning off. Everything's the same stuff.
So it just be
This on its own. Oh, on five. So then once you have on that on 20, you're going to take that and multiply by that.
okay.
Start with 3.
All right, thank you.
You have just on the 5, 20. I have a mug in my house. Well, I'm not a dad insofar as I know right now. Did you have to say that so far that you can't be? If you were a dad, that would not happen. I don't know now. If I were a dad, I might be dad. You have a question on this? Well, it's an external force of 3, you just multiply by 3. Yeah, on the left side. On the right side. I took the 2 out. What's usually? Yeah, so I took that.
Because it's like 3 times the.
Yeah. Yeah, so then you can say, well, like, getting exponential of last time. Yeah. Yeah, and your question, like, as written, you're saying I was looking at 1, but not 5.
So.
So it's not the same. Yeah, so you basically. Yes, right, yeah. Now, then you said rearrange for the volume. Yeah, rearrange for the volume. Or the bottom where it's bottom. Oh, yeah, sorry. So this is. Yeah, this term here comes from. It's a 1 0 0. So there. that's what it is, twice a month. So then, yeah, you see that on both sides.
Yeah, so it becomes. So here, it's external.
Yeah. Yeah, so. Stop. I mean, it's only slightly from the perspective of like, to now on the keyword. Yeah. Sorry. It's all, or that's. Yeah, so you are gonna think that. Whole part. But you actually really want to get as many points as possible. You either make it. Yeah.
Yeah, so
Yeah. Transform them there. Like, yeah. So just like with regular, I ask you to say, integrate, that's not fine. So you actually have to do it like that. That has to stay on. It'd be nice if.
Was this start what most of you have right now? So I talked to most of you at least once, and most of you got somewhere like right here at least. Is that okay with everybody? Now from here, you always sort of have to remember that like, even though it looks kind of messy, like there are obviously better ways to write this for other purposes. From the transforms perspective, it's always best to have things in as many pieces as possible, so you can just individually invert, go back to T. So, this looks kind of gross to me because normally you'd say like factor out this 2s squared plus 2 thing or something, right? You just write it once up front, you don't have to recopy it. But if you're trying to use the table to go backwards, this is actually a way nicer way to write things because you can just individually deal with this, individually with that, individually deal with that. So let me just pause here and see if there's any sort of confusion or disagreement about this. You can see if I made any mistakes or not. So we learned from last time, right, that the only one of you who's willing to tell me I made a mistake is Megan, but she waits like 5 minutes.
That's what I have.
Oh, all right, well, Jacob has this. If me and you both have it, what's the probability, right, that'd be wrong? Okay, so you guys want to start from here and start messing with it? Yeah. So now your job is to be like, well, I have 3 pieces of work here to do, right? Maybe let's start with the smallest one. A little scratch work here. Start small and then work up to the bigger ones, right? Okay, so let's think about 1 over 2s squared plus 2. I'm going to bring up the Laplace transform table. Okay. So anything of use from this table? Line 7, right? So use line 7, you have to think of that s squared as having a coefficient of 1. All right. Done? Okay, so now let's invert that piece. 1/2 what? Just sine t. Fine. Bless you. So hopefully in my solution, I have a sine t at the bottom. Do I? I get plus sine t. That's good. 1/2 sine t. All right. So that's working out pretty well so far. Okay. So let's just, I don't have so much board space. Let's just bank that piece. And for the remaining 2 pieces, if we can handle one piece, we can handle the other piece almost for free, right? Just gotta make some minor adjustments to it. Okay, so as we saw last time, that first term, say, really all we need to think about is inverting this. The 3 is just along for the ride. The e to the negative 5s, we have a theorem that just deals with that. It means you're gonna have a u5 show up and shove to the right by 5, So if we can invert this, then we're done. So this is pretty close to being invertible, but you gotta mess with it a little bit. What do you gotta do with that? Partial fractions, anytime it's factored, right? You ever have a factored denominator, you're like, oh, sweet. Wolfram can break this into pieces for me. I don't know what it is off the top of my head. Somebody have it?
Wolfram said it's 2S plus 2 over S,
which doesn't sound right.
S.
1 over 2s minus s over 2 times s squared.
Okay, so 1 over 2s, and then what was the other piece?
2 times s squared minus plus 1 is minus.
Like this?
Yeah, but it's the first one minus the second.
Oh, all right, so it's like this? Okay, so you may have typed it in wrong. Yeah, but this looks reasonable to me. So, I mean, what partial fractions does is it gives you two terms over here. One denominator matches the first denominator, and the other denominator matches the second denominator. Anybody else confirm this? Anybody else get something like this? Okay. All right, so now we got to invert these guys. 1/2 1 over s. Where does that invert to? Just a half. That's nice, right? Because 1 over s, if you look at the table, it's just 1. What about this guy here? S over s, 2s squared plus 2. Not 1 over, or whatever we used to have, right? So let's think about this as s over s squared plus 1 like that.
So 8.
So line 8, and what does it invert to? Yeah, it goes on just t here, right? Do you agree with that? You pulled the half out, and you're left just a 1 right there. So I think we just get a cosine t here. So see if you agree with that. Oh, sorry, I lost my half, right? What happens when you try to skip too many steps on these little boards, right? I did pull a 1/2 out, right? There's a half there. And now we're basically done, because now we say to ourselves, oh yeah, well, I didn't just want to invert that. I had, 3 e to the negative 5s there also. So we've done the hard work. How do we handle the fact that there's a 3 e to the negative 5s there? Yeah, so we do two things. We take what we had and we multiply by a u5, I guess, right? 5.
Would that be 3u5 or just u5?
Oh yeah, I'm sorry, my 3 is still there, right? So 3 is along for the ride. That 5 means a u5, and then what else happens here? Yeah, you just shove this to the right by 5. This. Which presumably is why at the bottom of the sheet, no? Did I close it? Yeah. I get something like this. So here's my e to the negative 5s piece right there, right? Actually, it's on the board. You see where the other piece comes from? Right, the e to the negative 20s piece is all the same, right? Just shove 20. This kind of thing is more like once you've done these enough, right? This is like maybe a 15-minute exam problem. Because there's not that much algebra to do here with Wolfram in your back pocket, right? If you got to do partial fractions on your own, then we're talking way longer. But Wolfram's doing all your algebra for you. Okay, any questions or comments on this? Okay, well, we should do a get check here maybe, right? So our story is we have a mass of 2, spring constant 2, no damping, right? Switch a flip at 3, sorry, it's on 5, and switch off at 20, 3 newtons. And there is some initial velocity, although no initial displacement, right? Does this look like it's reasonably modeling that story for you, the movement of that mass on the spring? Why is there a free floating sign that wasn't shoved? What's the deal with this? Why is that turned there? Yeah, the initial velocity gets things moving, right? Everybody see that? So if u prime of 0 were 0, we wouldn't have this term. So we'd have to wait till time 5 to see anything, right? Everybody see that? That's nice. So that part accords our physical intuition. And then what? At time 5, notice we get a 3/2 minus 3/2 cos thing, right? So at time 5, you start combining a 3/2 and a cosine with that sign you already had going, right? But then at time 20, this minus turns things off, right? So you get a positive 3/2 and then minus the 3/2, right? So things are sort of canceling out. Why are there no exponentials here? What's the deal with that? No damping, right? So the motion's not going to die. So again, all that accords with what we should have expected. It's just now the Laplace transform can handle having this kind of thing in your answer, right? So there's a lot of power here that we didn't have before. And that's how section 6.4 ends. Okay, so let me just pause here and ask, in the homework, can you handle something like this? Can you handle something like this, but maybe the numbers are a little nicer, right? Like what made this so bad? Well, actually, it was just this poor 2 right here, made everything terrible. Because we had to keep peeling 2s off of things, right? Which meant I had like down here, I had a 1/2, things like that. So something like this, do you feel like you can handle with, again, maybe some nicer numbers? Yeah. Yeah, so if you're asked to graph these things, I just want to sketch. So it doesn't have to be anywhere near accurate. You know, it has to be qualitatively accurate, you know. So when it comes time to think about what's happening here, really you just have to think about the story of the DE actually. And then you can later ask yourself, okay, the graph that I made, does it in some way track with this? But you're not really trying to graph this per se, right? So if you gave me this DE and said, graph the solution for me, I'd be like, all right, well, there's no initial displacement, no initial velocity. So at least initially it's not going anywhere, right? Oh, but then at time 5, 1 Newton shoots into the system. So it's gonna start moving. How is it gonna move? Well, anytime we have a constant force and there's damping, we always see this pattern of like where it's like, and then kind of the damping and the force kind of fight, you know? But the damping will still kill the motion, it's just not at equilibrium. But then, oh, that force gets turned off time 20, so there's nothing keeping it sort of up anymore, right? So it would swing back down and damping and kill the motion. So we saw the graph last time, but it looks something like this. Like time 0 to 5, nothing. And from 5 for a while, like here's the force and the damping kind of doing the work together, right? And then at time 20, you turn that motor off, there's nothing keeping it up here. So it's gonna have to sort of swing back and then damping will kill it. So if you just draw that, like on an exam, that's acceptable, you know. Probably, it's not literally correct, probably. Does that answer your question? Okay. So asking you to sketch a graph is just another way for me to sort of figure out if you understand the story behind this DE, you know. Like, can you tell yourself what's happening here, and then can you track the physicality of it with the picture? Other questions on this section before we move on? Okay, so before we leave the section, I should of course say, and this is an appropriate place to say it because I'm staring at this really terrible expression here. You know, one time we were having one of these picnics on the quad. Do you guys remember those? From the old days, right? And I was talking to somebody who had this class, and like it was 2 years after that. And we were talking about DEs, and I said something like, "Oh, did you like that class or whatever?" And he said yes. And he said, "But I hated the Laplace transform." And you know, sometimes like children or students say very hurtful things to you. Do you ever have that? You know, like one time my daughter said, "I hate you." She didn't mean it, but like I forced her to wear pants or something, right? And she screamed that. So I thought, why is the student telling me this hurtful thing right now? What did I do? You know? And I started talking to him about it, and of course you can see, right? Like basically his answer was, "Well, I hated it because of this," right? Like I didn't like all the details, and that's fine. But then I asked him, "Well, what was the Laplace transform for? Wasn't that a nice idea? You know, you remember what it was for?" And he said, "I don't remember the purpose." And then my heart broke even more, right? So when you think about like 2 or 3 years from now, what should your takeaway be? I mean, obviously you're not going to be writing this down, but you should remember that it exists to do this very powerful thing of dealing with motors that are turned on and turned off, or batteries that are attached and detached, right? That's a really nice thing. That's the big idea of a Laplace transform. That's why you care about it. So you remember that when you talk to me 2 years from now. And if you do remember, I guess you can still lie to me and just watch my little lip quiver a little bit. If you like that kind of thing, right? If you like seeing other people in pain. And my children do like that. They like seeing me in pain. I infer anyway. That's what they like. Okay, so the last two sections of the chapter are very short. As you can tell by looking at a clock, we're not going to finish it today, which is fine. But we can at least start section 6.5, and 6.6 is also very short. So we'll sort of finish these off on Monday, and then the rest of the week will be practicing with these problems, so that by the time you guys take an exam, it's just going to be smooth sailing, right? I'll be sitting at home watching Great British Baking Show, just 100, 100, 100, 100, right? That's what I like doing. Okay. So the point of this section is just to show you another kind of discontinuous forcing function that comes up in physics a lot, I am told. Yeah, I don't know any physics, but certainly if you crack open a physics book, you will see things like this for circuits and spring mass systems, the Dirac delta function. So this function here is just another way of having some sort of discontinuity in your system that chapter 3 couldn't handle, okay? So here's just more physics for those people who like physics, which I assume is all of you. Right, Jacob? You like physics? Oh, no. Sorry. Other Jacob doesn't like physics. That's all right. Okay, so, yeah. Where'd my eraser go? Okay, so first I just want to explain to you what this function is. And then once you know what the function is, if you can transform it, then you can just slot it into transform problem. And the transform just takes over. Same idea. Okay, so the Dirac delta function is a function with two properties. They're on the screen here, but I do want to write both of them down just for emphasis. Okay. So the first thing to know about the Dirac delta function is this. It's like almost always 0. Right? So for pretty much all the times ever, the output is 0. So if you were to graph this, can you picture what such a function looks like? What is it?
Straight line.
Yeah, it's just like 0. And then I didn't tell you what happened here, so let me just leave that open for now. It's like that, right? You agree with that? Okay. So this is one thing to know about it. The second thing to know about it is this. Leave my picture up. If you were to integrate it, so you look at the area under the curve. Area under the curve is 1. So what do you think about that?
Is that because there's no curve on it?
Well, I guess let me just focus on the area part, right? So I left a hole here, so I guess I could fill that in. Let me fill it in. Like, let's just suppose that the point's there or something, right? How much area is under the curve? Well, how much area though? None, right? So, I mean, what if I put the point like right there? You know what I mean? So, on the one hand, when you define this, your response should be like, I'm confused, right? Because how can the function be like 0 all the time, but you're telling me there's some area? And there's no, like, again, you can imagine getting some area like that, right? But it doesn't do that. It just stays flat. So the question is, how does such a function exist? What are the physicists doing? And physicists do all sorts of wacky things, right? Everybody knows that, right, Jacob? Other Jacob? Anyway, so the answer to the question here of like, how does such a function exist? What are you talking about, right? The answer is, well, how about you don't worry about that? You know, like quit asking. The answer is that when you call this the Dirac delta function, it's actually a misnomer. There's no function that does this, okay, as we just discussed. So it's more of like an idea that physicists can make rigorous if they feel like it, okay? But this is actually how they define it, you know, so I'm just sticking with their definition and your book's definition. So anyway, when you look at that, you're like, I don't know about all that. And then I say, why don't you trust me every once in a while, right? Isn't that what this class is all about? How about a little faith every once in a while, right? So for us, we sort of say, okay, I don't think this is actually a function, but whatever, really, this is all you need to take away from it. This function in quotes, models a large but spontaneous burst of force, okay? So we're not talking about flipping a switch and flipping it off like a minute later or a second later, whatever. What you have to imagine happening is you flip the switch on and you flip it off in the exact same instant, right? That would send a very large burst of force in there if the motor's big enough or something, right? But it'd be spontaneous because you turn it on and off at the exact same time. That's what it models in physics problems, a spontaneous large burst of force. So for literally an instant and no more than an instant, you're going to shoot some large amount of force into the system. And when you write it like this, T minus T naught, that's just a horizontal shove. So if you want to do this spontaneous burst of force to say 5 seconds, you put a 5 in there. If you want to do it at 30 seconds, you put a 30 there. Okay, but that's how you should read these functions in these problems. So if you see this showing up in a problem, you're like, okay, at time 5, this person like spontaneously punched that mass, right, real hard. It was just instantaneous, no motor being turned on and turned off. That's what this function does for us. Okay, so let me pause there and ask. Any questions on that concept? Okay, so physicists do lots of crazy things that mathematicians kind of squint at a little bit, right? Or scrunch our brows at. My favorite one is this. This is Friday Fun Day, so we have to have a little fun, right? Physicists will do things like this sometimes. Anybody seen this? Okay, so this is the sum I equals 1 to infinity of I, right? 1 plus 2 plus 3 plus 4 plus 5, right? If I ask you what this is, what is that? I mean, isn't it obviously this? Right? What else could it be, And physicists say, some physicists, hashtag not all physicists, right? Some physicists say, that's not infinity. It's negative 112. Ruh-roh, So there is a way to make this rigorous, okay? There is a way to make sense of this sum as negative 12. And it has something to do with quantum mechanics. But as soon as I say that phrase, I put up my hands and back away slowly, so I don't know what I'm talking about. But anyway, there's some physics textbooks you can crack open where you see that equality, Who knows what those people are up to, right? The Dirac delta function is just one of those things, right? Where you're like, okay, whatever, roll your eyes, right? Okay, so anyway, for our purposes, all we care about is it's a spontaneous burst of force, and if we knew how to transform it, we could slot it into transform problems. So here's a theorem that tells you how to transform it. Its transform is nice. It's a decaying exponential, but with no divided by s this time. So that means that algebraically, everything's going to go nicer. So if you like, this is like I'm using the book's notation, but this is like a minus c right there, and you slot in a c right there, right? So it transforms just like a u sub c, except there's no divided by s. Otherwise, it's the same. Is it okay with that? So just, again, not obvious, right? It's even less obvious now because, like, how do you even transform something that's not really a function? I don't know. But again, you let the physicists sort of figure all this out. Okay, so here's like a standard sort of homework question over this. So again, if you like the circuit problem, you can tell a circuit problem, but here's a spring mass story. So blah, blah, blah. We don't need to read all that out loud, but I claim that this paragraph gives you this initial value problem. So read the paragraph and see if you agree with that. Oh, yeah, we don't agree with that. That should be a y prime, right? Whoops. Everybody see that? Any other disagreements? With just this first step. Any other disagreements there? I mean, do you see where this delta's coming in, right? You see the English sentence that makes that show up? Right there. If you ever see that, right, that's saying use a delta function there. A large external force, instantaneous is the key word, right? No on and off, right? On off happens in the same instant. Okay, from here though, since we know how to transform that delta guy, this is all just the same. There's no new concept here or anything. Again, having a 2 here is pretty obnoxious because you got to peel it off and accept the consequences. But, you know, otherwise this work goes very similar to last time, but simpler because there's no divided by s. So let's just stop and ask like this equation here. Any issues with that? I transform both sides. Okay there. I isolated L of y and pulled the decaying exponential off and pulled the 2 off. And I asked Wolfram to complete the square, I guess. I did a lot in that one step. So let's stare at that and see if there's any disagreement there or any confusion there. This is actually probably just imported from the handout last time, right? We already dealt with this 2s squared plus s plus 2 guy, right? Is everybody okay with this? Okay, so now, like, I see this e to the negative 5s over 2 guy, and I know that I need to transform what's next to it, and then I can just do the shove thing, right? So I think about dealing with this, and again, I'm just stealing from what we had yesterday. So you need a root 15 over 16 up here, right? So you got to divide by it out front, and you end up with this coefficient here. So that's thievery from yesterday, but let's stop and see if you agree or disagree with that. If this would give you this. I mean, do you want to see any of the steps spelled out here, or are you comfortable with this being from Wednesday?
How do you get that 2 over root 15?
2 over root.
Oh,
this guy?
Step 5.
Yeah. So here, instead of a 1, you need the square root of this. So you got to put root 15 over 16 up here, like we did on like we did on Friday. So that's root 15 over 4, right? But if you put that up top, you have to divide by it outside to compensate. And dividing by it flips the fraction. Huh? So then once you have that, you got to remember you had it divided by 2 there, and the divided by 2 knocks this 4 down to a 2. So there's a 2 right there, right? Otherwise, though, you just take this guy, you put a U5 on there from the 5 there, and you shove it to the right by 5. So replace t's with t minus 5. And there's the solution. So this is a, you know, a less beefed up, right? Sort of a watered down version of the problem from last time. You were sort of doing an on-off thing, but it happened instantaneously, and it made the math a lot more streamlined. And for some reason, I'm pointing out to you, you can rewrite it like this if you want to, right? This function doesn't get turned on until time 5, so you can point that out if you want to, but this is how you normally write it. So there's a Laplace transform problem with one of these Dirac delta guys. Questions, comments on any of these steps here? Okay, so we have like 15 minutes left, but maybe we should just save this till Monday, I think. So maybe on Monday we'll start with this, and then section 6.6 is very short, so we can finish that off, and then maybe we'll have time to do some extra practice leading into the practice day on Wednesday. All right, so yeah, let's save this for Monday maybe. All right, you guys okay? All right, have a good weekend.
Thank you, Dr. McKeon. Have a good weekend too.
Hey, man, Pedro, do you have any questions on what we covered?
No, I